Hi everyone, and welcome back to Physics 11. So in this video, we're going to be looking at more sort of mathematical side of circuits. So in last video, we talked about how we can connect circuits, parallel and series. So today we're going to look more in depth at current. So for example, this animation on this title slide, we have electrons, so negative particles moving through a conductor, as you can see here. Over a period of time. So let's talk more about current. So many particles are either positively or negatively charged. The charge of a particle, we use letter Q, is measured in coulombs after a scientist named Coulomb. For example, the charge of a proton or electron is called the elementary charge, and it has a value of 1.6 times 10 to the negative 19 coulombs. So it's a very tiny little charge. Now, conventionally, we use positive value for protons and negative value for electrons. Now, because we're talking about current electricity, we're going to be talking about the flow of these particles, whether it's positive or negative. In our case, it's going to be negative. We're going to be talking about electrons. So it's going to be a flow of charge from high to low potentials. Now, this can also apply to positive particles or ions. So for example, when you study biology 12, you learn about potential differences, how, for example, the electric signal is transmitted in the neurons. It's going to be flow of ions, not of electrons. That's one of the nice things about circuits, is that a lot of the laws that you learn, they can apply to other types of circuits as well. So it's not just electric circuits, you can apply them to air circuits or water circuits or blood flow circuits. So all the rules are going to be the same. The units might be a little different, but the laws that you learn are going to be the same for all types of circuits. So talking about charges. So the number of charges flowing per second is defined by a specific quantity. We call this the current. So the current, we use letter I, is defined as the charge Q over time. So for time we use seconds, for Q we use coulombs. So again, the unit that we get for the current, we call this amperes, again in honor of the scientist Ampere, or amps for short. So again, I stands for current, which is coulombs per second, or amperes or amps, and we use capital A for that. Again, Q is the electric charge, measured in coulombs, and time is going to be measured in seconds. So that's the definition of current. It's going to be coulombs per second. So consider a river. The rate of water flowing down the river is its current. Now note that we talk about the rate of water flowing, not the speed that individual water molecules are moving. So the same is true for electric circuits, where the current represents how many electrons pass a certain point in a certain amount of time. So it's not how fast they're moving, it's how many of them are moving through a certain point. Now the current in the circuit depends on two variables. The first one is voltage. So voltage is the energy per coulomb given to an electron, and the units are volts. We use V for that. Lowercase, uppercase v, sometimes it doesn't matter. There's no other variables that we can confuse it with. So again, voltage is the energy per coulomb, so joules per coulomb. And resistance R is how difficult for the current to flow through a substance or a conductor. So the units for resistance are going to be ohms, again, in honor of scientist Ohm, and we use the Greek letter omega. So this is Greek omega. So Ohm came up with the law, which we call Ohm's law, which states that the voltage is going to equal to the product of the current times the resistance of whatever the conductor is. So we have V equals IR. Now we can, of course, then reorganize this and solve for I or R if we need to. So from this equation, we can get two more equations, basically solving for I and then solving for R. So this is called the Ohm's law. You might have seen it in your junior sciences, depending what you learned. So what else can we do? we know the Ohm's law. We can now solve for voltage, current, and resistance. So let's also talk about power. So we already mentioned power in the previous unit when we talk about energy, work. And again, we often talk about the amount of power used by electrical device, and this is often confused with either voltage or energy. Now recall the power is the rate of doing the work. So we have energy used per unit time. So how does that relate to electric power? So in circuits, we can define electric power as the product of the current and the voltage. So how do you get joules per second from this? Well, if you remember, we just defined current to be coulombs per time, right? So we have Q, or charges per time per second, and voltage we just said is energy per charge per Q. So we have joules per Q here. So we have J over Q here. So the Q's will reduce away, and you're going to be left with joules per second, which is going to be watts, which is power. So that's how you get electric power from the definition of current and voltage. Now, of course, we can do the same thing with this. We can solve this for I or V, which is basically just elementary operations here. But we can also take the Ohm's law and definition of power and combine it together to get two more definitions for power. So that's what I have on this slide here. So again, it says here, from the definition of power and Ohm's law, we can derive some formulas to describe the electric power. Now, in the middle here, just the reminder that power is defined as work over time or change in energy over time. And in this case, when we talk about electric circuits, the change in energy is the change in voltage times the number of particles Q, so coulombs. So we have the first definition, power equals the current times the voltage. And then we have two more. Power equals I squared times R and V squared over R. So how do you get the other two? Well, we have to use our Ohm's law. So Ohm's law states that voltage equals IR, and combine it with the definition of power. So for example, here we can solve this for V. Sorry, not solve for V, but replace the V with the definition of voltage from Ohm's law. And in this case, we're going to get P equals I times IR. So here, I times I, so we get I squared times R, and we get our middle equation here. So I squared times R. So again, using Ohm's law and the power definition. Now, how do you get the other one? Well, if you look at our Ohm's law, V equals IR, and we can replace, instead of the V, we can also replace the I here, right? So if you take your Ohm's law and you solve it for I, so I is going to be V over R. And then you take your power definition, which is power equals IV. And now you replace the I instead of the V, you're going to get V over R times V, which is going to be V squared over R. So that's how you get the last definition for power. So you have three definitions for power that we can use. So depending on the problem, in some of them you might be solving for voltage, and you only have the resistance, so you can solve for power that way. Or in other cases, you only have the resistance and the current, you can still get the power, right? So let's take a look at a couple of examples that we can solve now. So here's the first example. It says, an electric fan has a resistance of 12 ohm and requires 0.75 amps of current to function properly. What voltage is required to operate the fan? All right, so let's think of the definitions that we know. Ohm's law states that the voltage equals the current times the resistance. Now in this question, we're given the resistance and we're given the current. So you can write it out on the side. So R equals 12 ohms, so omega, and the current I equals 0.75 amps. Now the voltage is what the question is asking us for. So V is the missing variable. So in this case, we can get away with the Ohm's law and basically just use this, plug in the values for I and for R to get the voltage. So the I is 0.75 times 12 ohms. And again, this should have two suffixes in the end, so 0.75 times 12 equals to 9.0 volts. So that means that the fan needs 9 volts to operate properly. Okay, So this is a simple equation, a simple question with Ohm's law. So what else can we do here? Well, let's take a look at the next example. Here we have an electric heater that emits 100 watts of power that's connected to 120 volt power line. What is the resistance in this heater? All right, so what do we know? We know the power. So the power is 100 watt or 1.00. So let me just write it just 100 with the decimal there, so I don't have to write the times 10 to the second there. So what else we know? We know the voltage is 120. Okay, and we ask for resistance. So that's the unknown. Well, we can, if we go back and look at our previous slide here, we know the resistance, or we're looking for the resistance, we know the voltage, and we know the power. So we can use the third definition for power, V squared over R, to solve that example. So V squared over R is what we want. So you're going to say power equals V squared over R. And again, you don't need to memorize these. You can always derive them in case you need to. In this case, V is 120. And notice there's a decimal at the end, so that means that there's 3 sig figs. And the power, or sorry, the resistance there, no. So I got ahead of myself. So first, let's rearrange this for, so let's get rid of this for now. Let's solve it for R because we know the power, we need the R. So R is going to equal V squared over power. So now it's going to make more sense. So here we're going to plug in our voltage, which is 120 squared. Power is 100 watt. All right, so we get 120 squared, which is 14,400, divided by 100, which is 144. And the units are going to be ohms. All right, so now that you can do, now that you know the Ohm's law and the definition of power, you can do lots and lots of practice questions in this section. So if you have any questions from that practice section, make sure you post them as a comment in Teams.